Hi everyone and welcome back. On this video and the next one, I will try to explain curvature of space-time and how it involves the Riemann tensor. So without further ado, I will share my whiteboard and I recommend that you adjust the playback speed. So as usual, I have a problem with my pen. I'm sorry. Okay, now it wants to work. Great. All right. So today we will talk about space-time curvature. So, yeah, sorry. Space-time curvature as a result uh, of parallel transport and how it's related to the Riemann tensor. In parentheses. Okay. So one manifestation of curvature, we know it. We saw it already a bit when we talked about geodesics, is that if you enclose a loop, so you start from a point and you come back to a point, and along this loop you parallel transport a vector. If space-time is flat, the vector is going to come back parallel to itself, but if my sheet of paper is curved, so if my space-time is curved, and this is my initial vector A. After parallel transport, A might come back not parallel to itself, A prime. And so we see that parallel transporting a vector, it's a bit like applying a transformation, and the kind of transformation we will observe gives the kind of curvature, or how does it transform from A to A prime, tells you how on the path it is curved. All right. So this vector difference here that I will write delta A is proportional to a vector R, which is Riemann curvature. And I will just write here that Riemann curvature, it encodes how space-time is curved in all fourth direction, so time, x, y, and z, or if you're in spherical coordinate, for example, time or theta and phi. So the Riemann tensor encodes how space is curved in all those four directions. And we can say that it's an invariant local measure of curvature. All right. So this is a bit about like the concept of curvature and how does it involve Riemann tensor, but mathematically, how does that translate? How can we mathematically and rigorously write everything out and actually do some work, some computation? So we have a hint because here we're talking about parallel transport, and we know that parallel transport is related to a covariant derivative. We know that we can quantify the result of parallel transporting a vector by taking its covariant derivative. So this also we've seen in the videos of geodesics. All right, so let's do some math then. I will start with a brief reminder. So imagine that my white sheet of paper is my space-time, and I have a vector field in that space-time. Something, for example, like this. So I have a vector field in that space-time, and at point P, my vector field, I will call it V of x alpha. Okay, and I want to know how it's changing that vector field around the point P, and what I can do to know how much V is changing at this point is to ask myself, how does it change with some direction? So at point P, I'm gonna define a vector T, and now the covariant derivative T of this vector field V, this is gonna tell me how much V is changing at point P in direction T. And for that, I can define a geodesic in the space-time. So here is my flat sheet of paper. So I will do a flat line. That is a geodesic. And at some distance epsilon, from which we will take the limit, we will take epsilon goes to 0. So we are neighboring. At point Q, no, that's not that. I didn't work on this explanation. I forgot how to explain that. Okay. Hmm. Give me 1 minute, please. So you do have this vector field like this. You do have this vector field, and you do define a point P here at which the vector field looks like this vector that I just drawn. So you do have a vector field V of x alpha, and you do consider a geodesic as this one, for example, and of course this geodesic is directed by this vector t, which will remain parallel to the geodesic and parallel to itself along the geodesic. And you see that at point Q here, so you have VP here and VQ here, alpha, alpha. Yes, and now so what you do is that you parallel transport this V at point Q, you parallel transport it here. Yes. That's VQ alpha parallel transported to point P. And the result of that is quantified by the covariant derivative in t direction of vector field P at point P, which is equal to vector field at point Q parallel transported to P minus vector field at point P, divided by epsilon. And of course, I didn't write that we take the limit epsilon goes to 0. This, let's take another color. This difference, you can see that it's this, or maybe like that. I don't know. It's not very important. Ça n'est pas vraiment très important in English. You can leave this. Okay, let's carry on because getting really boring over here. So that was a reminder about the covariant derivative. Reminder nabla. Great. All right, so now let's carry on and do a bit the math. So you want to quantify curvature from parallel transporting a vector. Great, so we start by taking a vector at some point P naught. We start by taking, I should zoom in. Okay, so we start by taking at point P naught a vector A alpha. in a spacetime. Now we want to parallel transport it, so let's introduce how is it called? Coordinate system, but don't remember how we call it in GeoRes. Just a minute. Yeah, coordinate base. Okay. So I introduce this is the line of v constant. So this will be v equals 0, and this will be v equal some delta v. I don't know, 1v. That won't make sense. Okay, and these lines, no, almost. Right, and this line are the line of constant u. So this is u equals 0, and this is u equals some delta u. So this is a coordinate frame with some vector basis u alpha v alpha. Here, of course, u alpha equal 1 0, v alpha equal 0 1, but if you want to define them, then you can write it like that. This is just a more complete definition in case you're using Cartesian coordinates. Okay, so those are your coordinate vectors. And now before we start to parallel transport A alpha from P0 to P1, P2, P3, before we do that, we need a tool. We need to introduce an auxiliary field that will exactly match A alpha at point P0. Right, I go again, like that. Okay. And everywhere else, we don't care so much. Maybe we look like that here. Okay. A parallel transport A alpha along this V equals 0 line to point P1, A alpha. Yeah, my pen is not working. Great. It's fine, it's gonna work when it will want to work. Okay, it's working now. Great. Yes, so this was A1 alpha, and now no, A0 alpha, and now we parallel transport, and we obtain A1 alpha here. And I'm going to write it here, A1 alpha. Okay, so we've parallel transport A alpha, right? And we see that this in green. So we had also B0 alpha here. Here in green, we see that we have B1 alpha. At point on P1, we have a B1 alpha that is not matching with A1 alpha anymore. And we have a vector difference here. That is delta B alpha from 0 to 1. Okay. And so we can write our parallel transport vector. No, thank you. Okay. We can parallel transport, no. We can write A1 alpha equal B1 alpha minus delta B0 1 alpha. Let me think. Yeah, here I have to inverse. It should be like that. Okay. Yes, but what is this that I'm writing and I haven't defined it? What is this? This is so we can say that A1 alpha, because A0 alpha was equal to B0 alpha, when you parallel transport A0 alpha, you obtain A1 alpha. You can say that A1 alpha is equal to B1 alpha. You can say that it's equal to B1 alpha minus the covariant derivative of the vector field B alpha at point V equals 0 in the U alpha direction. So here it will be too much alpha, so I will call it U beta direction, and for length delta U. So here it's delta U multiplied by delta U to parallel transport all the way to this point B1. Yes, so we can say that A1 alpha is only, we can write it in only in terms of the auxiliary vector field B that I have introduced, because they match at the very first point. Yes, you can say that A1 alpha equal B1 alpha minus this delta minus this current derivative times delta u of the vector field p alpha. Yes, it does make sense. And so indeed, by Schall relation, you see that this is just this vector. Okay. Right. So you keep doing that. You parallel transport to P2 to P3, and then you come back to P0. So you keep working on that. And at the end, what you get is that, no, thank you, is that A for alpha equal, well, this is A prime alpha, A 0 prime alpha. It's just once we looked, we come back here with A prime alpha 0, okay? And this is equal to P alpha 0 minus delta P from 0 to 1 alpha minus delta P 1 to 2 alpha minus that's delta P from 2 to 3 alpha minus delta 3 to 0 alpha. Yoo-hoo, we're all happy. P alpha 0, this is just A alpha 0, they're the same. Okay, so we can write delta A alpha, which is what we are interested in. It's the transformation that is going to give us the kind of curvature. This is delta A alpha. We can write that it's equal to A prime alpha minus A alpha, both at point 0, okay, equal blah blah blah. I'm not going to rewrite it, it's just written here above. Okay, and then you can factorize everything like that, dividing by, no, delta V minus delta U. And when you take the limit, you take the limit, delta V goes to 0, delta U goes to 0, because that's what neighboring is. And so you obtain du dv v gamma covariant derivative. Oh, no, it's not writing. My pen is not writing. U beta All right, so here we had, yeah, whatever. So we have a covariant derivative of a covariant derivative minus a covariant derivative of a covariant derivative. Great. If we work on some algebra and symmetries, we see that a lot of stuff are gonna cancel out. Okay. And so what we obtain is delta A alpha equal delta is du dv u beta u gamma. Okay. We see that this is antisymmetric in beta gamma. So it's gonna pick up only the antisymmetry part of this in beta gamma, and it will be equal to the enclosed area, the area we enclosed in our loop, delta S for surface or beta gamma. Okay. And if you keep working, so now if you yeah, so this is an operator. This is an operator. It's crazy because oh, so it's an operator acting on the vector field P alpha. And so if you let it operate, you will see that this in fact is equal to a tensor. So a lot of bisymmetry with the Christoffel symbols that are in the covariant derivative bisymmetry. A lot of things are gonna cancel. And you will find that this operator acting on the vector field P, which is an auxiliary vector field that we introduced, is in fact equal to a rank 4 tensor called the Riemann tensor beta gamma delta. So we still have the enclosed area bar loop delta S beta gamma times our initial vector A delta. So this is the Riemann tensor. And A delta was the initial vector when we unclose our loop. So what we see is that an operator acting on the vector field is actually equal to a Riemann tensor. So a rank 4 tensor contracted with the value of that field at point P. Contracted because delta, they're contracted indices. The Riemann tensor at one point contracted with the value of the field at one point. And that's the first way to characterize the Riemann tensor. It is as a result of parallel transport. Yeah, space-time curvature.